Mastering Algorithm Design. Strategies for efficient problem solving in the world of computer science. Algorithm design stands as the cornerstone of solving computational problems effectively. Whether you're building software, optimizing processes, or tackling puzzles, understanding how to craft efficient algorithms can mean the difference between success and failure. This guide delves into the nuances of algorithm design, equipping you with the tools and mindset to approach challenges systematically. Efficiency isn't just about speed, it encompasses resource management, scalability, and adaptability. By mastering algorithm design principles, you'll unlock the ability to create solutions that are both robust and performant. From sorting routines to pathfinding algorithms, the right approach can transform your code from functional to exceptional. Understanding the core principles of algorithm design. The foundation of any great algorithm lies in its principles. These guiding tenets ensure that your designs are logical, scalable, and maintainable. At their heart, algorithms aim to solve problems by transforming input data into desired output through well-defined steps. A primary principle is correctness. An algorithm must produce accurate results regardless of input size or type. Without correctness, even the fastest algorithm serves little practical value. Next comes efficiency, which measures how well an algorithm uses resources like time and memory. Balancing these factors ensures your solutions remain viable across diverse scenarios. Scalability is another crucial aspect. As datasets grow, an inefficient algorithm may falter under pressure. A scalable design anticipates future demands and adjusts accordingly. Finally, clarity plays a role in maintenance and collaboration. Well-documented, readable algorithms reduce errors during implementation and debugging phases. Correctness ensures reliable outcomes for all valid inputs. Efficiency minimizes time and space complexity for optimal performance. Scalability adapts gracefully to increasing input sizes or complexities. Clarity facilitates easier understanding, modification, and reuse of code. These principles form the bedrock upon which all successful algorithmic solutions are built. Applying them consistently leads to resilient and adaptable systems capable of handling evolving challenges. Common algorithmic paradigms and their applications. Designing algorithms often involves leveraging established paradigms. These approaches provide structured frameworks for tackling recurring types of problems. Familiarity with these paradigms allows you to select the best fit for your specific challenge. One widely used method is divide and conquer, which splits a problem into smaller subproblems until they become trivial to solve. Classic examples include merge sort and quicksort. Another popular technique is dynamic programming, ideal for problems exhibiting overlapping subproblems and optimal substructure properties. Fibonacci sequence calculations and shortest path finding algorithms frequently employ this strategy. The greedy algorithm paradigm makes locally optimal choices at each stage, hoping to achieve a globally optimal result. While simple, it doesn't always guarantee perfect solutions but excels in certain contexts like Huffman coding or minimum spanning tree construction. Lastly, backtracking explores potential solutions incrementally, abandoning paths that fail. Early constraints, a staple in combinatorial optimization tasks. Selecting the appropriate paradigm depends heavily on the nature of the problem itself. Understanding when each applies helps avoid unnecessary complexity or inefficiencies later stages of development. Evaluating time and space complexity. An essential skill in algorithm design is evaluating time and space complexity accurately. Knowing whether your solution operates in linear time or exponential time informs decisions regarding feasibility and scalability before writing any code. To assess time complexity, consider how execution time grows relative to input size. Common notations include constant, O(1), logarithmic, O log n, linear, O n, quadratic, O n squared, polynomial, O n to the power of k, and exponential, O k to the power of n, runtimes. Similarly, measuring space complexity reveals how much additional memory your algorithm consumes compared to input dimensions. Benchmarking becomes invaluable here. Comparing theoretical estimates against empirical measurements validates assumptions made during analysis. Tools like profilers help identify bottlenecks and optimize poorly performing segments within implementations. Optimization efforts shouldn't solely target worst-case scenarios either. They must also address average-case behavior relevant to typical usage patterns encountered daily by end users. Data structures. Choosing the right tool for the job. Data structures serve as containers holding information manipulated by algorithms. Selecting suitable ones significantly influences overall performance metrics associated with proposed solutions. Different structures excel differently. Arrays offer fast indexed access but lack flexibility when resizing dynamically. Linked lists allow easy insertions/deletions but require extra overhead maintaining pointers between nodes. Hash tables enable rapid lookups at expense of increased storage requirements due to collision resolution mechanisms employed internally. Trees organize hierarchical relationships efficiently, supporting operations such as insertion, deletion, and traversal, especially useful in implementing binary search trees or B-trees commonly found within database indexing schemes. Graphs model interconnected entities perfectly suited for network flow analyses or dependency graph traversals utilizing DFS/BFS techniques. Making informed selections hinges largely upon anticipated operations performed repeatedly along with expected dataset characteristics, influencing choice towards array-based versus pointer-linked alternatives based purely on operational frequency alone. Iterative refinement through prototyping. Prototyping provides opportunities refining initial ideas iteratively toward final product versions meeting defined specifications precisely. Starting small enables identifying flaws early, preventing costly rework cycles downstream after full-scale deployment occurs. Begin by sketching out rough outlines, visualizing high-level logic flows, then gradually flesh out details, adding layers functionality, progressively enhancing capabilities bit by bit. Testing prototypes against sample inputs verifies alignment expectations set forth initially, thereby reducing risk and countering unexpected behaviors post-launch phase. Version control practices assist tracking changes made, allowing rollback whenever necessary, preserving historical records, facilitating collaborative environments involving multiple contributors working concurrently, improving quality assurance standards inherently. Feedback loops formed between testers/users play pivotal roles, shaping direction taken next iterations, ensuring continuous improvement cycle perpetually enhances end-user experience while simultaneously addressing emerging concerns raised spontaneously throughout lifecycle development process. Handling edge cases and corner scenarios. Robust algorithms must handle edge cases gracefully, avoiding crashes or erroneous outputs triggered unexpectedly. Identifying these situations requires thorough consideration, possible boundary conditions likely occurring during runtime executions. Null values represent common sources trouble, particularly when dealing unvalidated user inputs susceptible containing missing entries. Implement defensive checks verifying presence mandatory fields prior attempting manipulations thereof, prevents exceptions thrown otherwise disrupting normal operation sequences. Overflow/underflow issues arise frequently. Numeric computations exceeding predefined limits, imposed system architecture restricting range allowable numbers, stored variables declared fixed size, primitive data types rather than arbitrary. Precision equivalence available, higher level languages offering automatic expansions automatically. Testing suites incorporating extensive unit tests coupled fuzz testing methodologies increase chances detecting subtle bugs. Slipping past manual inspections alone would miss easily overlooked corner scenarios requiring specialized attention devoted exclusively uncovering hidden defects lurking beneath surface appearances initially appear benign. Performance optimization techniques. Once core functionality implemented successfully verified correct functioning, remaining task focuses optimizing existing solutions, achieving better efficiency levels surpassing original benchmarks established. Earlier stages project timelines. Caching represents powerful optimization strategy, storing previously computed results, eliminating redundant recomputations, subsequent identical requests arriving thereafter, conserving valuable CPU cycles otherwise wasted, recalculating same answers repeatedly unnecessarily. Parallelism leverages multi-core processors distributing workload amongst several threads executing independently, accelerating completion times dramatically, especially applicable compute-intensive applications benefiting greatly concurrency. Features supported modern hardware configurations readily accessible to today's marketplaces. Code profiling identifies hotspots consuming disproportionate amounts resources, enabling targeted improvements, focusing areas yielding highest gains, return investment spent, tuning related components, ultimately resulting noticeable enhancements. Perceived performance objectively measured quantitatively, instead relying subjective impressions alone. Integrating machine learning concepts into traditional algorithms. Recent advancements, artificial intelligence, open new avenues, integrating ML models alongside conventional algorithmic constructs, creating hybrid solutions combining strengths. Both domains synergistically complementing each other, mutually beneficial ways. Supervised learning techniques, applied pattern recognition tasks, augment traditional classification algorithms, boosting accuracy rates. Achieved pure rule-based systems, unable to discern intricate correlations, embedded complex datasets inherently challenging human analysts perceive intuitively without explicit guidance, provided training samples annotated meticulously beforehand. Unsupervised methods cluster similar items together, assisting recommendation engine implementations, suggesting products customers might appreciate despite limited direct interaction histories. Recorded databases typically sparse, lacking sufficient quantity. Meaningful interactions required, forming coherent associations reliably. Reinforcement learning offers exciting possibilities, autonomous decision-making scenarios where agents learn optimal policies, interacting dynamic environments, receiving rewards, penalties according actions undertaken, pursuing ultimate objective, maximizing cumulative returns accrued throughout extended engagement periods. Real-world examples demonstrating effective designs. Consider Google's PageRank algorithm revolutionized web search ranking. Pages-based link popularity reflecting authority weights assigned hyperlinks pointing toward particular documents, thereby determining relevant scores. Displayed search results accordingly. Amazon employs recommendation engines predicting customer preferences, recommending items aligned interests, generating personalized shopping experiences, enhancing satisfaction levels, consequently increasing sales conversions. Translating positively, bottom line financial figures reported, quarterly earnings statements released publicly annually. Netflix utilizes clustering algorithms grouping viewers' watching habits, enabling suggestions tailored individual tastes, promoting retention rates, keeping subscribers engaged long durations, mitigating churn risks, threatening business sustainability. Prospects negatively impacting revenue streams. Edge computing shifts processing closer devices, reducing latency, enhancing responsiveness. Mobile applications demanding real-time interactions, benefiting augmented reality, virtual reality, immersive experiences, requiring minimal delay, rendering frames smoothly without perceptible lag, affecting user immersion, negatively detracting enjoyment. Derived interactive sessions conducted remotely, distant servers located geographically dispersed regions worldwide. Sustainability considerations increasingly influence design choices, prioritizing energy-efficient algorithms, lowering carbon footprints, produced digital infrastructure consuming vast quantities electricity, powering data centers, housing cloud services consumed billions watts power annually, necessitating conscious efforts minimize environmental impact, caused unchecked growth, demand constantly rising exponentially year over year. Conclusion: this guide explored fundamental aspects of algorithm design, highlighting key principles, paradigms, evaluation criteria, and optimization techniques. Mastering these concepts empowers you to tackle complex problems confidently, crafting solutions that balance correctness, efficiency, and scalability seamlessly. As technology evolves, staying curious and adaptive is vital. Continuously refine your skills by experimenting with new paradigms, studying case studies, and engaging with the vibrant AlgoHey community. Your journey into algorithm design is just beginning, and the possibilities are endless.